Now in this session we talk about dynamic modeling of the pool process. So that's regarding the chlorination of the pool. So mainly the focus is on the use of the conservation principles, more specifically the conservation of mass, the component balance equation. Now if you recall the pool problem, there are two pools, pool 1 and pool 2. Liquid is coming in, that's water coming in pool 1, the overflow going to pool 2, and there is another inlet in pool 1, and there is outlet from pool 2. Now if you look at the chlorination problem, we'll make some assumption that the chlorine is coming as part of this inlet flow where the chlorine concentration is C1I, and the chlorine concentration is this tank is C1, chlorine concentration in this tank is C2. We'll also assume that this one is pure water coming in. So if you have something like C2I, it's 0, and obviously this is C1. Okay. Now look at the problem from specific control perspective. So what we want to observe or what we want to predict from this model. So that defines the modeling objective, which is the step 1. So step 1 is the define modeling objective. So for this case, if you want to find the concentration of chlorine in tank 2 when there is a change in the concentration C1I. Do remember that for this case we are not considering there is a change in the flow rate, but we are considering there is a change in the chlorine concentration in the inlet flow. So we want to find a model between C2 and C1I. Now for our case, this is the output. This becomes somehow, we'll call this input or disturbance, because so you may need to find the model between input and disturbance. So typically concentration is not something that you can directly manipulate, so that can be considered as a disturbance. So you have to find the model between these two variables. Okay. Now step 2 will be to gathering some information about the process. So for detailed modeling, we will need the process dimension, pool size, density, and other properties as well, fluid properties. But for the time being, let's concentrate on what's the process knowledge we need is how these two variables are related. So you know that for these two variables, if there is a change in C1I, that will affect the concentration in the pool, which is C1, okay? And then when there is a change in C1, that will affect C2. So you know that we may need two equations to describe these two relations, okay? Now the step 1 and step 2 is done. The third step is, what's the main step in the modeling exercise, which is the develop model equations. Now we'll start with the conservation principles. We see that for this case, there is nothing regarding the temperature, so conservation of energy will not be relevant for this case. Also, we don't have anything related to momentum, so we'll discard that as well. So we're left with the conservation of mass, and for this case we see that there are two components, water and chlorine, so this component balance equation will be relevant. But what about the overall mass balance? So let's take a look at we call this the overall mass balance. Now overall mass balance, you know the equation, accumulation equals in minus out. So for this case, we see there is no change in the, so for pool 1, definitely there is no change in the level. So if you recall from our previous experience, it will be simply F1I will be F1O for the pool 1 example. Now for pool 2, you see that there is no change in F1I and F1O. So in this case, there will be no change in the level as well. So if you write down the equation, it will be simply so we are assuming there is no change in the flow rates. So that leads us to this equation. If there is a change in F1I, that would lead us to an accumulation term for pool 2. Okay. Now our focus is more on the component balance. So if you look at the component balance equation, so if you look at the term, so accumulation, again I am using a simplified form, only saying accumulation. It should be proper, it should be rate of accumulation of component I. So for I component, any component I, here we will see this one will be our chlorine. So when I write accumulation, read it as rate of accumulation of chlorine in tank equals in, out, generation, consumption. So again, rate of accumulation of chlorine in tank either in 1 or 2 equals rate of chlorine coming in minus rate of chlorine going out plus rate of generation of chlorine minus rate of consumption of chlorine. Now for this case, we see that okay, there is no reaction here, so this term becomes 0 and this term becomes 0. So we have only chlorine in and out. So let's write it for the pool 1 part then. So for pool 1, rate of accumulation of chlorine will be, so suppose this C is expressed in terms of mass fraction. So the mass of chlorine in tank A, which is rho V1, that the mass of total liquid, C1, mass of chlorine, rate of change with time equals in will be the mass of liquid coming in times the concentration liquid minus mass of liquid going out times concentration C1. Okay. So this one is in here and this one is out for pool 1. Okay. So carefully look at this equation. We are saying that okay, C1, C1I, C2, all these are in terms of mass fraction. So we have rate of accumulation of mass in will be total liquid times mass fraction, that will give the mass of chlorine, and then its rate of change with time, that gives the accumulation time. So these two together gives you the mass of liquid coming in, and with the mass fraction, that's the mass of chlorine, mass of liquid going out times mass fraction, and that gives the mass of chlorine out. Again, the generation and consumption terms are not there because there is no reaction involved. Okay. Now we write the same equation for pool 2 will be again rho V2 C2, its rate of change with time will be coming in. There are two streams coming in here, F1 naught and F2I. So it will be rho F1 naught C1 plus rho F2I C2I minus rho going out is 1 F2 naught C2. Okay. Now see, we'll need some sort of assumptions to finalize this equation. Now we are considering for this case that the chlorine concentration is really very little, and what is true for like this pool type of problem. So we'll assume that the concentration of chlorine does not change in the concentration of chlorine does not change in the density of the liquid in the pool. So we'll make the assumption that rho remains constant. Also, we have made the assumption that this C2I, so the second stream coming to the pool, that's pure water, there is no chlorine there. Okay. So C2I equals 0, that's another assumption we already made. Now if we make this assumption, and for this constant cross-sectional area for this pool, we'll end up getting, considering that the volume of liquid remains constant for both of the tanks, there is no change in the inlet flow. So assuming this constant and V1, V2 remains constant, do remember that if there is a flow rate change F1I or F2I, that will lead to V1 and V2 to be function of time. So that needs to be considered. So if we use this assumption, this from this pool 1 problem, finally we get, we'll have rho V1, rho, this rho gets cancelled, V1 gets out. So we'll have V1 dC1 over dt. Now again, I'm writing this now in terms of time, equals, so rho got cancelled, that F1, I'll call this F1I equals F1O. If I simply call this to be F1, using two terms, I'm using the one term. So F1 C1I minus this F1 again F1 C1. And for pool 2, we'll get again V2 So you can just simply rearrange this equation. So after some sort of rearrangement, we can get for these two pools, we'll have write in some sort of standard form in a way. So to write it as dC1 dt plus F1 over V1 C1t will be again F1 C1I, this is a function of time. And the second equation will write simply this way, d C2t over dt plus, you see here F2I here, so this F2O over V2 again C2t will be this F1 C1, so F1 over V2 C1t. Now these two together formulates the Model's equation, model equations for this case. And now if you can relate it to the two links we established, so this one shows the relation between C1I and C1, and this one showing the relation between C1 and C2. Okay. So from a differential equation perspective, from the first equation you will get C1, and then from the plug in into the second equation you will get C2. Okay. So that's one example where we used only the component balance equation. We used the overall mass balance, but that didn't have any effect on the dynamic response of the process. Okay. So this is one example, a simple example to explain the concept of the component balance equation to derive a simple model of the process. So you see how to use the same concept for a reactor problem when there will be temperatures involved as well. Now for this pool problem, this problem can be made further complicated if there is a change in F1I as well. That will make a change in the pool level, and that will, in that case, we'll have to use the overall mass balance equation in combination with the component balance equation to get the complete equation for the process. Thank you.